Okay, welcome to the final video for chapter 7. Once you've completed this video, you can then have a go at exercise 7F and the mixed exercise 7, combining everything we've looked at in this chapter. So connected particles, this will help with your work at the end of year 1 applied as well. And essentially you're going to have things connected by light, inextensible strings, and the essential part of that is that the tension is constant throughout. So rather than having two tensions, we have the same tension appearing in both of the equations for our particles. So for example 11, let's get on with the examples and see what questions get raised from that. So we have two particles, P and Q, of masses 5 kilograms and 10 kilograms respectively, are connected by a light, inextensible string. So the key part of this is that the tension that's pulling that particle up the slope is the same as the tension that's trying to stop that from falling down. Okay, that's why it's a light, inextensible string, because the tension is constant throughout. So rather than having a T1 and a T2, we have the same value for T. So essentially we have one unknown and not two. Now we're told on this one it passed over a smooth pulley, slip of the tongue, which is fixed at the top of a rough inclined plane. Okay, so once again it tells us, as we had in the last video, tan alpha is 3/4. That's a 3, 4, 5 triple again. So whenever we need it, that means sine alpha is 3/5 and cos alpha is going to be 4/5. And the forces acting on our diagram here. So if we start with particle P, we've got the tension that's pulling it up the slope. We have our weight directly down of 5g. We have a reaction force at right angles to the motion, and we are told it's a rough plane and the coefficient of friction is 0.2. So we can say straight away that our friction force is 0.2 lots of R. And our acceleration is going to be measured up the plane. Particle Q is much simpler. We've only got the two forces, the tension that's trying to stop it from falling and the weight of the particle, which is 10g. And again, because it's a light inextensible string, whatever the acceleration of P up the slope is, that's going to be the same as the acceleration of Q downwards there. So again, T is the same as T, A is the same as A, and that's the reason we use the fact it's a light inextensible string. So first of all, we need to find the acceleration of the system. So it's quite straightforward again. There are three equations which we might not need to do all of them. Okay, but if we do, you're going to have F equals ma for P in the direction of motion. You're going to have F equals ma for Q in the direction of motion, and we can resolve at right angles to the motion for P as well, so we can find out the value of R. And again, our angle alpha is going to be tucked in there. So first of all, if we look at particle P, if we do F equals ma in the direction of motion, we have that T minus 0.2 R minus the component of the weight, which is 5g sine alpha, is going to equal 5 multiplied by A. And then if we resolve at right angles to the motion, we can then find out the value of R. So R is going to equal 5g cos alpha degrees. And then if we look at particle Q, F equals ma again in the direction of motion. So we're going to have 10g minus T. 10g minus T is going to equal 10 lots of A. So if we want to find the acceleration of the system, then we can see very clearly, if we find out a value for T by substituting our R value into there, then we can put everything together. So you might find in some of these questions as well that it's easier to find things in the other order. That's fine too. So if I make T the subject of this equation, so I've got T is going to equal 10g minus 10a, and we know that R is 5g cos alpha, then I can substitute T to replace T there, substitute R to replace R there, and I'll have an equation with A. So we've got 10g minus 10a for T, minus 0.2 lots of R, which is 5g, and remember cos alpha is 0.8, minus 5g times sine alpha, which is 0.6, and that equals 5 lots of A. So if we work out that on our calculators, divide everything by 5, you end up with the acceleration in the system is going to be 4.1 meters per second squared, again just given to two significant figures. And once you've got A, obviously we can substitute the exact value into there. So T for part B is going to be 10 lots of G minus 10 lots of A, and that gives us a value of 57 newtons to two significant figures again. Now, the reason I'm going through question 12 is because you get an interesting question for part C. The first part is quite straightforward because, in fact, it's easier because in this question we've got a smooth plane, so there is no friction. So it makes the work on particle A a little bit simpler than we had before. So again, we have our tensions. For B, we have our weight of 5G. And then for A, we just have a reaction force, and we have our weight of 2G and our angle of 30 degrees in there. So we have one less equation to do here because we haven't got a friction force in terms of R, so we don't need to find out what R is. So for this question, if we look at particle A first of all, we've got that F equals ma, remembering to write exactly what you're doing so you get method marks in case you make one silly mistake. So we've got T minus 2G sine theta, which in this case is 30 degrees, is going to equal the mass times acceleration. And if we look at particle B, remembering that our accelerations are up the plane and straight down there. So if we look at B, we've got that F equals ma in the direction of motion. We're going to have 5G minus T equals 5 lots of A. So we basically need to find the acceleration in B, okay, and then the tension in the string. So if we use the fact that we know from equation 1 that T is going to equal 2A plus 2G sine 30 degrees, then we can substitute that value in to replace T. So we've got 5G minus, remember to put that in brackets so you don't forget the second negative. So 2G, well, sine 30 is a half, so that is just going to be G. So 2G times a half, which leaves us with G. And that's going to equal 5 lots of A. So we have 4G minus 2A equals 5A. So we've got 4G equals 7A. So A is 4G over 7 meters per second squared, which is what we were asked to show. And then the tension, obviously we can substitute our value for A now into there. So our tension is going to be 2 lots of 4G over 7 plus 2G sine 30 again, which is just G. And our value for the tension, therefore, is going to equal 15/7 of G. Now for part B, if I just flick back very quickly, it asks for how you've used the fact that the string is inextensible in your calculation. So as we've said in the previous example as well, that means that the tension is constant throughout the string, or you could then say that the acceleration for A is going to be equal to the acceleration of B, something along those lines. Now the final part, this is the reason, it's asked for the force, the magnitude of the force provided by the string on the pulley. So if we highlight this area here, because the tension is constant throughout, the tension in the string is also providing a force on the pulley in that direction and that direction. Okay, so our resultant force is going to be in that direction. Okay, and we know that if that is 30 degrees, then this angle here is going to be 60 degrees. So I therefore know that's going to be split because these tensions are equal to each other in that direction there. So the force in that direction, okay, is going to equal, if I just pull that down here now, you're going to have T cos 30 plus another T cos 30. So the force on the pulley is going to equal 2T times the cos of 30 degrees. So we've got 2 lots of 15/7 G, because that's the value for T, times by the cos of 30, which is root 3 over 2. And that will give us an answer of 15 root 3 over 7 lots of G, because the 2's cancel out. And obviously the value there is in newtons. So just be aware, obviously the tensions here are equal and opposite. In the first part of the question, normally we're looking at the tensions acting on our particles, hence they are those two. But if you are asked for the force of the string on the pulley, then you can see, therefore, that the tension is equal and opposite, and that's how we find out the force when you're asked that question. Comes up not too regularly, but from time to time as a final part to a question. So now you have everything you need to know to complete the final exercise 7F on connected particles, and then try your luck with the mixed exercise 7, which combines everything. And it's been a lot of work in this chapter, so remember all the statics examples with ladders, and then the dynamics, and then obviously finishing off with dynamics with connected particles too. So best of luck with that, and I'll see you at another exercise shortly.